You ever just stop, look up at a massive skyscraper, and just wonder? These things are giants of steel and glass, and they seem to totally defy gravity. But how do they do it? Well, today, we're going to pull back the curtain and look at the incredible engineering that makes these modern marvels actually work. I mean, seriously, how does a building that weighs hundreds of thousands of tons manage to just stand there? It's not magic, not at all. It's actually this brilliant system of design. And the secret isn't what you can see on the outside, it's what's hidden deep inside. And that's the key, right there. A skyscraper isn't some big, solid block. It's an elegant, incredibly powerful skeleton, where every single piece has a very, very specific job to do. If you can understand the skeleton, you'll understand the whole building. So here's what we're going to do. We're going to go on a little journey, starting with why steel is the perfect bone material. Then we'll look at the joints that hold it all together. We'll get into the simple push and pull that every piece endures, how they handle massive loads, and the safety rulebook that engineers swear by. By the end of all this, I promise, you are going to see these buildings in a whole new way. Okay, let's start at the very beginning. Why steel? Why not super strong concrete or wood or something else entirely? Well, the answer is in this unique combo of properties that makes steel pretty much the perfect material for building tall. Now, what's so cool here is that it's not just one of these things. It's all three working together. Yeah, high strength is a no-brainer. It can handle incredible forces. But ductility, that's its ability to bend and kind of stretch without just snapping. That's absolutely crucial for safety. And maybe most important of all, its behavior is incredibly predictable. Engineers can calculate its limits with almost perfect confidence. All right, let's move on to the joints and how this whole skeleton is held together. I mean, think about it. A skeleton is totally useless if its bones aren't connected properly, right? In a building, these connections are everything. So, a connection's main job is to transfer force smoothly from one piece of steel to another, say from a horizontal beam to a vertical column. And here's the golden rule. The connection has to be just as strong or even stronger than the parts it's joining. It absolutely cannot be the weak link in the chain. And here we see the two main ways engineers connect all that steel. You can either bolt it or you can weld it. Bolting is kind of like using a giant high-tech assembly kit. It's super fast and efficient to do on the construction site. Welding, on the other hand, literally fuses the steel into one single piece, which gives you that clean, seamless look. Each one has its place in the engineer's toolkit. Now, when you're bolting, the details really, really matter. A simple lap joint where you just overlap two plates can create this little off-center force that tries to bend the connection. But engineers have a really clever solution called a double cover butt joint. They basically sandwich the main plates, which keeps all the forces perfectly aligned and gets rid of that unwanted bending. It's a game of pure geometric precision. And with welding, the shape of the weld is critical. The most common type is the fillet weld. It's this strong triangular bead of metal that's laid right in the corner between two pieces of steel. But for that seamless, this was always one-piece look, engineers use a butt weld, which joins two members end to end. I mean, every single millimeter of these welds is designed and calculated for maximum strength. Okay, so we've got our material, we've got our joints, now let's look at the bones themselves. See. Every single member in that steel skeleton is designed to do one of two basic things: resist being pulled apart or resist being pushed together. That's it. So first up, we've got tension members. Just picture a rope in a game of tug of war. Its only job is to resist being stretched and pulled apart. In a building, these members are designed to handle huge stretching forces. Engineers have to calculate their strength against a few different failure modes, like the steel stretching too far, that's called yielding, or the connection points literally tearing out, which is known as rupture. The total opposite of tension is, you guessed it, compression. These members, like the huge columns holding up a building, are constantly being squeezed, and their biggest enemy isn't what you'd think. It's not being crushed into a pancake. It's a much more sudden and way more dangerous type of failure called buckling, where the column just suddenly bows out to the side. So how in the world do engineers predict and prevent this? Well, the key is a simple but really powerful calculation called the slenderness ratio. Imagine trying to crush a short, fat log versus a long, thin stick. The stick is going to buckle in a second, right? The slenderness ratio just puts a number on that idea. It's a measure of how long and thin a column is. Based on that ratio, engineers use specific formulas to figure out the actual safe stress the column can handle, which is always less than what the steel is truly capable of. The more slender the column, the more they have to back off that stress to keep it from buckling. We've talked about pushing and pulling, but what about the parts of the skeleton that have to carry weight from the side? Well, that's where beams come into play. Beams are the horizontal workhorses of the whole skeleton. They stretch between columns, and they carry the weight of, well, everything. The floors, the furniture, the people. They resist all these loads by bending. But just like with columns, the way they can fail is often pretty surprising. Now, you'd probably think the biggest danger for a beam is that it'll just snap in the middle. But for a lot of long steel beams, the real risk is that the top part of the beam, which is being compressed, will try to buckle sideways. And when that happens, the whole beam can twist out of shape. This is exactly why engineers talk about beams being laterally supported, like when a concrete floor slab stops that twisting, or unsupported, which need a much, much more careful design. So, with all these crazy ways for things to fail, buckling, twisting, snapping, how do engineers guarantee a building is actually safe? Well, they follow a master philosophy, a kind of golden rule for all structural design. This simple little formula is the heart and soul of modern structural engineering. Design action is basically all the possible forces a structure might ever see: gravity, wind, you name it. Design strength is the calculated capacity of that beam or column to resist those forces, and the action must never, ever be greater than the strength. And this shows you the beautiful logic behind it. It's called the limit state method. First, engineers figure out all the forces. Then, and this is the critical part, they multiply those forces by a safety factor, just to be sure, to account for anything unexpected. And then, they design the steel member to have a strength that is comfortably higher than that beefed-up force. It ensures there's always a safe margin. So, now that we get the paces, the material, the joints, the forces, and the rules, let's zoom back out and take one more look at our skyscraper. When you look at a building's frame now, you can see it all happening. Those big vertical columns, they're compression members designed against buckling with their slenderness ratio. The horizontal floor beams, they're busy resisting bending and twisting. And those diagonal pieces of cross-bracing, they're acting like taut ropes, tension members, keeping the whole frame from swaying. And at every single intersection, the connections are flawlessly transferring all those forces through the system. You see, a skyscraper isn't some static, lifeless object. It's a dynamic system. It's a symphony of pushing, pulling, and bending forces, all held in this perfect, calculated balance. Every single piece is playing its part. It really is an incredible feat of science and ingenuity, and it's hidden in plain sight all around us. So the next time you walk past a construction site or you just look up at the skyline, you won't just see a bunch of steel beams. You'll see the skeleton, and you'll understand the symphony.